Right, so I thought next thing we better attack the big one, the biggie, which is add with carry, which we haven't got around to doing any arithmetic things yet. I think this is going to be quite a tricky one, and it's probably going to take more than one video, but I thought for the first one I'd just try and explain what's going on with add with carry and why it's more complicated than probably all the other instructions that we've done in the simulator so far. All it really does is it adds two numbers together, but it also adds a carry bit on as well. So that's the important thing to note there. And also to note that you can't add without carry. You have to clear the carry bit. So you always add with carry with the 6502. There's only one way to do it. And it says it there, this instruction adds the contents of the memory location to the accumulator together with the carry bit. I believe that is what I just said. But it's also, it's got all these addressing modes, which is fine. We've done these before. But if the overflow occurs, if an overflow occurs, the carry bit is set. And this enables multiple byte addition to be formed. So we can have a look at how that works. And that's it there. Carry flag is set if there's an overflow. Zero flag is set if just the A register is 0. And that would be, that would be after the add has happened, I assume. This instruction adds the contents of the memory location to the accumulator together with the carry bit. Yeah, I assume that zero flag is set after the addition. The negative flag is set if the bit 7 is set, because that's our bit that represents negative in this particular CPU. And the weird one, and this is the weird one, is the overflow flag, which is set if the sign bit is incorrect. So we have to account for the fact that this can add signed numbers together. So a lot of the time you're just treating numbers like unsigned, but you can add signed together, and you can get errors when signed numbers overflow. And in those cases, you've got to set the overflow flag correctly as well. So we can have a look at that, how that works and how I think it works anyway. And then in the next video, we'll have a go at implementing this. But maybe it's just worth going over, I've just got this whiteboard, I've got Microsoft Whiteboard. So maybe it's just worth going over how add with carry is going to actually work. And then we'll have a go at it in the next video. So let's just imagine that there's no carry bit for now. And let's just, what is the simplest way we can add two 8-bit numbers together? What's the simplest sum we could do? So it'd probably just be a 1 plus 1. So let's try that. So let me just, I'm doing this with the mouse, by the way. I don't have a tablet pen. I did have one, I gave it away. So you'll have to excuse my horrible zeros and ones, but this is what they're going to be. 6, 7, 8. So there's a 1. And let's just add that to another 1. There we go. And I don't know if there's an easy way to draw lines in here, but here we go. Right. So 1 plus 1 in 8-bit binary. How hard can this be? So the only thing we need to know to add together in binary is we need to know that nothing plus nothing is nothing. That's pretty much true in every number system, I think. 1 plus nothing, oh, that was a big plus, is 1. Nothing plus 1 is 1. And that's also true in almost all number systems. And the final one is 1 plus 1. Remember, this is in binary, is 1, 0. So that represents 2 in binary. So though that's all we need, binary is so simple, that's all we need to know to add these numbers together. And then once you know that, the rest of the addition is just the same as when you do decimal adding like you did in primary school. So in this case, the complicated one is first. We go from the right to the left, just like you do. 1 plus 1 is 1, 0. So I put the 0 there and I have to carry the 1 just like you do. So I carry the 1 down here. And then the next column I add together, including the carry. So 0 plus 0 is 0 because we've got that there. And then 0 plus 1 is 1. So we get a 1 there and there's no carry anymore. And now we just get 0 plus 0 all the way across the board. 0 plus 0, 0 plus 0, 0, 0, 0, 0. Cool. So 1 plus 1 is 2. We got the answer 2. That is super cool, super easy. So if there was if carry bit wasn't in existence, then that's all we'd need to know. So what we want to try then is what happens if we do an addition and the it would cause the number to get bigger than 8 bits, or bigger than a number we could fit into 8 bits. What would happen then? So we can do that quite easily. Let's just assume we have a number that's all ones. So that's the number we start with, and let's just add 1 to that, because that's enough to overflow this, or to get it outside of the 8-bit range, because we can't get an answer to that sum, not in 8 bits anyway. Oh, I've done that wrong. I'm going to add 1 to it. There we go, 1. So this is exactly the same as before. We'll just add this stuff together. We're just ignoring the fact that there's a add with carry. We're just doing add at the moment. So we take 1 plus 1, and that's 1, 0. So it's 0 there, carry the 1. And then we get 1 plus 1, so that's 1, 0. 0 there, carry the 1. 1 plus 1, that's 1, 0, carry the 1. You get the idea here that this is actually just going to be this all the way along. And then 1 plus 1, 0, carry the 1. And now on the last one, we've got 1 plus 1 is 1, 0. We get 0, and then we have this 1 that we stick outside, and that's the carry bit. So we actually got the answer 0. We added 1, 1, 1, 1, 1, 1, 1, 1. We added 1 to it, and we got out the answer 0, which looks like, that's totally wrong. Like, it's not the correct answer. But what we did get was we got 0, but with a 1 carry. So this is the number that we put into the carry flag. So that is the carry flag. So the 6502 has a carry flag, and if we did this sum, we'd have to put a 1 in there. And in fact, if we did this one, we'd have to put a 0 in there, because there is no carry from this one. So that's the carry from that sum up there, 0. So we'd put a 0 in the carry for that, and we put a 1 in the carry for that. So in effect, this actually is the right answer. The right answer is 0 with a 1 carry. And the reason why that's good is because actually add with carry does add the carry on at the start. And that means that you can chain these 8-bit sums together, and as long as you're adding the carry in, you can actually add like 16-bit values or 24-bit values or 32-bit values, and it can just go on forever. You can add as many as you want, and eventually at the end you have to stop, and you may or may not have a carry at the end, which you then might have to say, well, there's now an overflow that I can't deal with. But that's the same in any computer system, really. So in effect, what really actually happened with these sums was we started with 1 plus 1, but we were actually adding the carry bit in as well. And there was actually a 0 carry on that and a 0 carry on that. So if we wanted to, if there was a 1 in the carry when we started the sum, let's do this one. We could do this one again. There could actually be, for instance, let's try the 1 plus 1 again. So we have, let's do 1, 3, is that 7? We do 1 plus 1. That is a terrible 0. Try to do these fast and it just doesn't work. And it's possible that we had an overflow of a 1 from a previous calculation. And that basically gets treated, just added on with the initial calculation like that. So it basically becomes that sum. So actually to add up correctly in binary, we have to know not just how to add these 4 things, we have to actually know how to add 1 plus 1 plus 1, because that's the most complicated one that we actually have to do. And 1 plus 1 plus 1 is 1, 1. That's basically 3. 1 plus 1 is 2, plus another one is 3, and that's 1, 1. It's represented as 1, 1 in binary. So that's our first one here, that's what we'd get if we were adding 1 plus 1, but we already had the carry flag, because remember it's add with carry. And in fact, let's make that clear up here by putting it in the correct color. Add with carry. There you go, there's the carry bit. So, or carry flag, or whatever you want to call it. So 1 plus 1 plus 1 is 1, 1. And then we get 0, 0, 1, that's just a 1. And then these are just zeros all the way down, like that. So our actual answer to the sum in this case would be 3, which makes sense because we've got a 1 plus this carry bit, which gave us 3. So that could have been the high byte of a 16-bit calculation or something like that. And that would have worked out just fine. So basically that's how add with carry works, is that you add the carry on at the start and you spit a new carry out at the end. Again, this would have spat a 0 out at the end here, That would have been our carry bit from there. So the carry would have been left, it would have started at 1 and it would have finished at 0. So that's actually perfectly fine. Now the only other problem that we've got is, so that's how we're going to do the add anyway. And this is just assuming that these are unsigned numbers. But actually, there is the concept of signed numbers in the 6502. And the signed number is represented by the last bit in the 7th bit in the number is actually the signed bit. If that's set to 1, that is basically a signed number. So you can still do the addition exactly the same. This is my understanding of it anyway. So I'm going to do the sign bit in green. So if I put a 1 there, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So this is a signed number because it's got this 1 here. I'm just putting it in green to show that that's the sign bit. And I think that's actually, what is that? That is, you can actually do it in here. 1, 1, 2, 3, 4, 5, 6, 1. It's, that's not right. Yeah, there we go. So I'm representing that as a byte. So that's minus 127. So that's how that's represented. I think when all the bits are filled, that would be, if you get FF, that's minus 1. And as the bits go and start filling into 0, that gets you further and further to the lower end of the byte. So that's actually minus 127. So that's fine. So yeah, and then basically we could say, we could actually, we could add 1 to that. So let's put a signed number down here. Let's add 1 to this and let's see what we get. So let's just pretend that it's like normal signed number now. Okay. So we'll assume that there's a 0 in the carry up here, so we're not going to carry anything. So 1 plus 1 is 1, 0. That's 0 plus 1 is 1. We get 0, 0, 0, 0, 0, and a 1. So actually, let's do that one in green. So that actually shows that whatever we did here, we actually got, and this is plus 1. Whoops, wrong color. This is plus 1. The number we're expecting is minus 126. Now we know it's a minus because we've got the number there. I suspect that this is minus 126, and we can put it in here and find out. 1, 1, 2. Oh, it's not 1. Yeah, it is 1. 1, 1, 2, 3, 4, 5, 6, 7. Minus 126. There it is. So even though we kind of like treated it like a signed number, this actually worked out completely fine, and we had no carry at the end on that one. There was nothing to carry. So that was our carry flag at the end. So in effect, whether these are signed or not, it doesn't actually matter that much to you. You can treat them just like signed or not. You can add positive to negative and negative to positive. Now that would all be absolutely fine, apart from the fact that set if the sign bit is incorrect, the overflow flag. Now that's the problem here, is that you can get this signed overflow, and if you get the signed overflow, it means the result is wrong for if you were doing a signed calculation. So you have to set this correctly. So one of the ways you could see this happening is if somehow we did these signed calculations and this got messed up somehow. Now how could this get messed up? I mean, one of the ways you could see is if we added two negative numbers together. If we took a negative and we added a negative. So if you add a negative, that's just like, it's just the same as doing the subtraction, isn't it? So it's a bit like doing negative minus a number, and you should always get a negative number out of that. So that makes sense. If you do a positive and you add a positive to it, this is the opposite, then you'll always get a positive number. So a negative added a negative always gets more negative, and a positive added to a positive always gets more positive. And if you do anything else in between, you just get a mix. So you don't know what you're going to get. If you add negative and positive, you might get positive or you might get negative. But what you could guarantee then is that if you ever did one of these calculations and somehow you managed to get negative plus negative equals positive, that would definitely be wrong. So there would be something wrong there. And if you did positive, oh, that's the wrong color. If you did positive plus positive and you got a negative, then that also must be wrong. So that's the case that you've got to handle with this overflow flag. It's designed to tell you that if you were trying to do a sign calculation and something's gone wrong, it's gone overflowed out of the sign calculation, then that flag tells you that it's not correct anymore. And we should be able to engineer a situation like that reasonably easy. If we took, we could take, the biggest number we can represent is minus 128, and that is the one, the negative flag set, and they're all zeros, I believe. So I think that is minus 128. That is the smallest negative number that we can set. So if we add a negative number to that, we should get an even more negative number, but we will overflow because we can't go to minus 129 or 130. It just doesn't work. So if we want to add minus 1 to this, minus 1 is all the bits set, and you can think about that as if you took 0 and subtracted 1 from it, it would wrap around to FF, and that would set all the bits. So that's one way of remembering that. So minus 1 would be, wrong color, 1, 2, 3, 4, 5, 6, 7. So this is a calculation that will definitely, it's a signed number, and you could see that this would overflow even if it wasn't signed, if it was a signed number. But this is going to cause some kind of overflow, and we can recognize that if one of these conditions happens, I believe. So we just do the calculation like normal. We just do our binary adding. Let's assume that there's nothing in the carry bit there, so we're not adding anything on. Don't need that circle, but yeah, we're not going to add any carry bit on. We're just going to assume it was 0 from the previous calculation. So 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1, and this goes round and round and round until eventually we get to here, and we go 1 plus 1 is 1, 0, so that gives us a 0 there, and we carry the 1. So our carry flag gets set to 1, but if you notice, look what's happened. The negative bit has flipped. So what answer did we actually get here? I think we actually got, if you look at this as a signed number in the 6502, this is actually 127, I think. Let's do it on the calculator. Let's type 127 in, and there it is. It's 1, 0, 1, 1, 1, 1, 1, 1, 1, and that has gone wrong. So that has overflowed. So we didn't, if you were trying to add some negative numbers together, and you got minus 128 and you added minus 1, you would expect minus 129, but actually you got 127. You know something's screwed up. So this is the case. One of these conditions has happened. We took negative plus negative and we got a positive number out. So that is when we set the overflow flag. So overflow flag gets set here. So it's like a signed overflow. Overflow. So that is, that's what we do. We have to set that bit. So that's just telling you that your signed calculation has gone wrong. And you can see that if you were treating these as signed numbers, so let's imagine that we weren't treating them if you're treating them as unsigned numbers. If you were treating them as unsigned numbers, this would be 128 because it's just that bit set. All these bits here are 255, and what you'd end up with is 127, whoops, but you'd have your carry bit as well. And in this case, that's correct, because if you actually stuck the carry bit on a 9th bit there, we could do that in the calculator. Let's do that. Change this to word. So that would be, let's go to binary, be 1, 0, 1, 2, 3, 4, 5, 6, 7. And if we look at that, that actually gives us 383 in decimal. And let's actually try it. Let's actually try the actual calculation. 128 plus 255 is 383. So in effect, if you were treating this as an unsigned number, it would be totally correct to get the value 127 with a carry in. And if you were treating it as a signed number, you've got the answer 127, but you've got this flag to say, actually, your calculation has gone wrong, and you need this flag to know that that has happened. You have overflowed, and your answer is not 127. So the answer you've got in there is wrong. And the reason you'd need to do that is because the last bit here is the sign bit. You can't just like stick this on the end like you can with the carry flag. You'd have to do something else there. So what you would do would be up to you, really. But you might have to change how you thought about this number. So, I mean, really, you wanted a minus 129. So I don't know what the representation for a 16-bit version of this would be. You'd have to put this bit over on the bit 15 or something. But at least you know that, oh, my calculation has overflowed. And we could probably engineer this in the other direction as well, can we? So let's assume let's just see that the other version of this works. So if we had the biggest number we can represent, if we are doing positive in positive numbers, is 127, I believe, and we've actually got that there. So that's like the largest signed positive number that we can represent. So let's take that. Let's imagine that's one of the things for our calculation, and let's just add 1 to that. So we'll go 0, 0. Oh my God. 0, 0, 0, 0, 0, 0, 0, and 1. So we're going to take a positive and a positive. And what are we going to get? I mean, the number we expect is 128. Now we can represent that as an unsigned number, but we can't represent it as a signed number. So that's the important thing to get from this. So again, we can just do our calculation like normal. Again, I'm going to assume that there's nothing in the carry. So we do 1 plus 1 is 1, 0. 1 and 1 is 1, 0. 1 and 1 is 1, 0. 1 and 1. This keeps going. And then 1 and 1 is 1, 0. And then 0 and 0 and 1 is 1. So the answer we actually got was 128. Now, if that was an actual unsigned number, we actually don't care. I mean, maybe I should just draw these as in green as well, because we are treating them like the sign bit. So let's imagine we wanted to treat them like the sign bit, but we're saying this is positive. Now, if we did this as signed, we'd get this answer. But actually, remember, if we do 1 and all zeros, that is actually the real answer to that. If we're doing a signed addition, the real answer is that's minus 128, isn't it? So the answer we actually got out, again, if we're assuming this was, I should draw this as the sign bit there, shouldn't I? Let's do that. In green, that's a 1, and that is a 0. So if we treated this as the actual signed number, the answer we actually got here was minus 128. Now, as you can see, again, this breaks our rule that we did positive plus positive, and we got a negative out. So again, this has to set the, didn't put anything in the overflow flag this time, but it does still have to set, it didn't set anything in the carry, but it still does have to set the overflow again on this one, because this one overflowed if you were treating it as signed. If you weren't treating it as signed and you were doing an unsigned number, your calculation is actually perfectly correct, because you got 127 and you added 1 and you actually got 128 if you're just treating that, if you're assuming that isn't the negative bit. So I think these are the cases where we have to set the overflow flag when we thought if it was being treated as signed and we got the wrong result out. So I think given all that I'm probably going to do it in the next video now, but that is enough information to work out how to do add with carry. But how crazy is that? Have I missed anything out? I don't think so. So we just have to, I mean, setting the negative and the zero flags is something that we do all the time when we do these anyway. It's just that it's just setting this overflow. If bit 7 overflowed, the carry flag is set, and if the overflow flag is set, if bit 7 is wrong. So bit 7 is wrong, which is the negative flag, then we set overflow. But if bit 7 overflowed during the calculation, we set the carry flag. I don't know if that has been explained very well, but I think given, if you look at all this, this is what we've got to implement, the add with carry. So this is probably this and subtract with carry are probably the most complicated ones, I reckon. And you can see why, because you've just got to get these flags right. Otherwise, the people who write programs or written programs in the past for this won't know if this whole thing is working correctly. So I'm going to implement it like this. If I've missed anything out, I'll probably find out along the way. But I think for the overflow flag, these are the cases I've got to handle where we did a calculation and we got the wrong negation at the end. So I'll tackle add with carry in the next video, and I'll catch you then.